everybody.
Hello.
Welcome, Dr. Wang Likai, right?
Yes, correct.
And also Dr. Chen. So let me just have a quick introduction. So welcome everybody to today's session for computational beam sharing. So we are very pleased to have two professors today. As I mentioned, Dr. Wang Likai, who will be presenting on his Agile performance-based building, matching, design, optimization, and exploration, which is very interesting and linked to what Dr. Chen is also going to present on, which is Python for building design. So what we have is a usual 15 to 20 minutes sharing session, first started by Dr. Wang, and then after that followed by Dr. Chen. After these sessions, then we will have a Q&A for around 15 minutes where you can ask questions regarding their presentation. Okay, so without further ado, I will let Dr. Wang share his screen and start the presentation.
All right, so you can see my screen right now?
Still in the midst of sharing.
No?
Not yet. It just say it has started screen sharing, but it's black.
I guess in the meantime.
Yes, we can see now.
You got the wrong screen that's being shared. We are seeing your screen instead of the presentation screen.
All right. How about now?
Yes.
All right. So, all right. Thank you, everyone, and good afternoon. And thank you for the Aloysius hosting this event. And my name is Nikai Wang from the National University of Singapore. And now I'm a postdoctoral fellow here. And before I came to NUS, I am studying at the Nanjing University in China for my PhD degree. And during my PhD program, I developed this tool called Evomass for the building matching design, optimization, and exploration. So today I will just briefly share the major function and some example of Evomass in this sharing. So the background of the development of the Evomass is and over the past few decades, the sustainability and low energy building becomes a quite important topic in the architecture design and architecture industry. But most of the so-called high performance building is design is M&E dominated. So the architect actually just play a very trivial role in the whole design process. But we still have some quite successful example in the world that we can use the architecture design to achieve good building performance. I guess for a moment that most of the designer or the architects already use technique like building performance simulation in their practice. However, only using the simulation can just review the design problem, but provide no solution to the designer. So in the maybe like 15 years ago, the computational design optimization have been introduced to the architecture design research, I guess, but in the application is still very little application now. I guess the previous two sharing by the Thomas Workman and the Patrick Jensen is already covered this thing a lot. So I just briefly to summarize here. So the whole computational design optimization can be considered as a very efficient and scientifically more reliable design technique than the manually trial and error design process. However, using the traditional or the conventional automation process still have their own limitation because the technique is actually more focused on the problem solving rather than help the designer in the design exploration. So here is a very typical process of using the computational design automation. Firstly, the designer need to conceive their own design concept based on the design condition and the brief. Let's say the designer want to use the courtyard to improve like a natural ventilation or the daylighting, and then they need to encode their concept into a parametric model and then to run the optimization and get the result. However, because the parametric model only specify a very unique design strategy, the courtyard, so the optimization result just give the best shape of the courtyard to the designer. But for the early stage of the at the beginning of the architecture design, maybe the more important question is that whether or not I should use the courtyard, or if I can use the courtyard, whether or not it's a 3 smaller courtyard or 1 large courtyard is better for the building performance. So for this question, these kinds of the parametric model and optimization cannot give you the answer. So so behind this, the major challenge is the parametric modeling, because even nowadays, many young designers can build a very complex parametric model to generate some very fancy or very interesting building shape. But in terms of the building typology, they actually just specify very one design building typology, either a high-rise tower or some middle-rise building. However, for the architecture design, especially at the beginning of the architecture design, many research already indicate that the designer is actually more looking forward to the divergent design exploration. So I guess most of the designers have the experience that at the beginning of the design, we actually will propose multiple design solutions rather than one design solution. And then we try to compare and try to understand the trade-off and to also understand the hidden implication of the design problem rather than we just go very deeper to one design solution. So in order to support this kind of design exploration process, I developed the Evomass. The Evomass have 2 major components. One is for the design generation and other one is for the design optimization. And the combination with other simulation tool can be form iterative circle for the design optimization. So there are 5 key points of the Evomass. The first one is it is a very easy to use and integrated design tool in the Grasshopper. And the other one, the second one is that they have a very high reusability. You can use it in different types of the building design tests. For example, like a high-rise tower or the middle-rise commercial complex, something like that. And then the Evomass is aimed to produce optimization results of higher design diversity, and which can facilitate the architects to extract more information from optimization result rather than just keep them a very specific one. And the fourth one is that the Evomass is trying to provide designer with design information rather than a specific solution. We don't want to replace the role of architects in the whole design process, but try to just provide them some assistance in their decision making. And the last one is that using the Evomass, we envisage that can enhance the human-machine co-evolutionary design. So the design process of the using Evomass is something like that. The designer, because the designer do not need to do the parametric modeling, the designer only need to use to specify some parameter based on the design test and to control the overall feature of the generated design by the design generated by the Evomass, and then run the optimization, and then they can analyze the result and then to choose whether or not to develop this design or try to redefine or reformulate the whole design problem. And in this sharing, I will majorly to present the mechanism behind the design generation part. For the design generation, the Evomass using 2 principles called the subtractive and the additive form generation principle. And as an architect, I guess many of us can understand that using these 2 principles, you can describe almost every building in the world. So the idea behind the Evomass, if we can reversely encode these 2 principles, it means that we can use the parametric model to generate all the building that can be described by these 2 principles. So this can provide the Evomass a very great design variability and diversity for the design generation. And so for the parametric modeling, it's quite simple. We're just using the Boolean union and the Boolean difference to create the two algorithms. And then we also have some hard constraint in the algorithm because the two principle is not just specifically for the architecture design, they can also use in the furniture. So we need to make all the design generated by the Evomass can satisfy the basic architecture constraint. For example, the Evomass not allow the building floating in the sky. It doesn't make any sense from the architecture point of view. And also we have some other operator like the alignment. Alignment means that we can merge some small mass into one large unit. So using this way, we can create a very diverse a way to diversify the solution space. For example, for the courtyard design I just mentioned, like using this way, we can generate using one algorithm to generate the design with couples of the small courtyard or one large courtyard. So this means that the organization can search different types of the design alternative in the design space delineated by the Evomass. And from the design space point of view, you can see that the simple parametric model is just like a left-hand side. Each of the design, the parametric model is actually just define one design space, only specify one design strategy, for example, like a courtyard or the solar envelope. And then you can use like using a large algorithm to combine this algorithm into a combinatory parametric model. But the problem is that all the design generated by this combinatory parametric model only specify one strategy because you cannot merge the strategy in the two separate subspace. So for the subtractive and the additive algorithm, because the two algorithms doesn't describe or embody any specific design solution. So all the design strategy or the solution is actually deduced by the designer's reasoning. So the organization just give you the shape, and then what is the implication behind the shape is actually extracted by the architects, not the computer. So here is some simple example I can show you how you can use it. For example, in this example, we put the building in the urban context and in China. So we try to minimize the solar irradiation in the summer and also maximize the solar irradiation in the winter. So we run the optimization, and then we can see in the bottom of the page, you can see the 6 design, and all the design have a void in the left-hand side. So you can see that this actually indicates the cell shading strategy. However, an important factor here is that you can see all the voids on the left-hand side rather than the right-hand side, because in the right-hand side of the building is already have a high-rise tower. So the high-rise tower already block a lot of the some light. So it will be less efficient if you put this void in the right-hand side. So after you get the result and you can understand, oh, this is like indicates the cell shading, you can further develop the design, or you can transfer to like an external shadings design based on the information extracted from the optimization result. And also because the two algorithms, the generative algorithm, have quite diverse great design generative capability. So you can change some user parameter to make the design goes to different direction. For example, here using the same optimization objective, but you can see that all the design is focused on the vertical element rather than the horizontal element. And you can also use this result to understanding it actually also indicates the cell shading strategy. And then you can change to the objective to the like a daylighting, and then you can see all the void is facing to the north because the building in the north will be brought a lot of daylight for the facade, the north facade of the building. So if we can have a larger spacing with the north building, you can have a better daylight accessibility for the overall daylight accessibility for the building. So we are now already applied the Evomass into some studio design project for like this one is a educational building design, and the student first using the Evomass to run optimization for the single objective like daylighting and the solar irradiation and get the information. For example, the daylighting, the design solution is indicate like shallow floor plan and the courtyard, and for the solar irradiation, they have a step volume of the building because the building need to escape from the context shading caused by the surrounding building. So after that, they get the result. They try to run multi-objective optimization, try to combine the building feature into one design, and then they just using the multi-objective optimization as a form-finding approach, and then they get the result, and then they make a tweak based on the information they extract with the single objective optimization and finish their design. And this one is a design that finished by the 5-day workshop in the last year's Digital Future. And I won't go into this one, but just show you that even in the 5-day workshop, the designer can already use the Evomass in a quite design process. And this one is different from the previous one. This one is a design. The student first only focus on the building performance. However, the result, the solution of the design is quite optimization result is quite boring. So they try to embed some design intent into the optimization. For example, they want to have a more rooftop terrace for the people who use the building as a viewing and rest, and also some semi-outdoor space for the entrance. So they define, and also they want to minimize the sunlight block to the public park in the northern, in the north-hand side, in the north of the building. So they combine all these objectives to make run the optimization, and then you can see that the building can satisfy most of their objective. The shallow floor plan can ensure that the building have a good daylight accessibility, and also you can see a lot of the rooftop space and also the semi-outdoor space in the entrance. And also you can see the building and its right hand side have a lower in the height because it can reduce the sunlight blocked by the building. But in the left hand side, you don't see this strategy because the sunlight is already blocked by the high-rise residential building in the north. So it will be also less efficient if you lower this part of the building. And this one is for a high-rise building. Firstly, the student use the Evomass to do the massing study, and then they run normalization. For this design, the student try to minimize the context shading for the surrounding building. So you can see the design is to reflect the strategy of the solar envelope.
If I can attend, then okay. If I cannot, then never mind.
Sorry?
You all mute your microphone.
All right, let me continue. So you can see that all the small mass is actually hiding in the shadow casted by the largest one. So in this way, the building can minimize its overall shading on the surrounding urban area. So this one is a design conducted by a student from Taiwan. He tried to using the Evomass to achieve different design architecture language like a TVR and puzzle, and then to run normalization result. It means that actually they try to define 3 different more specific design space, and then to try to find the best solution from each of these space. And this one is a research we are now doing is that to combine the Evomass with the facade. We're using the cell additive algorithm to generate the facade, and then we try to, let's say we generate implement-free algorithm to generate free facade pattern, and we run the optimization. And using this optimization can provide you the information, the interrelationship between the building massing and the facade. For example, if you're using the facade with greater capability of the shading, you can see the building massing will put less compromise on the daylighting. So the building have a shallow floor plan, something like that. But if you're using the facade that is a weak in the shading, you can see that the building need to play more role in the reduce the solar exposure. So all the building massing will tend to have a very deep floor plan and to achieve like a cell shading strategy. And the last one is a design abstraction. The previous example is all show the design, the student just using the design generated by the Evomass. But the idea behind the Evomass is that the designer should not use the design generated by the Evomass. You need to extract the information and try to digest it and to combine with your personal preference and or your own design language into and conceive the new design. So this is the part we cannot do because student is quite maybe less experienced in the design. So I guess for the practitioner, maybe more easy to jump out of the design generated by the Evomass. So for the moment, the Evomass can be downloaded on the Full Rhino, and it's a free. And also, if you are interested in the mechanism or the some theory behind the Evomass, you can find the paper on the ResearchGate and also a lot of the tutorial on the YouTube. And here is a very short demonstration on how you can use the Evomass. Okay, I guess. Let me see. All right, I guess the video is broken, so we just skip the video and just go to the last pages. The last pages is that we are now already collaborate with some design firm in China, and we are using the Evomass for some primary and kindergarten design. But now since I'm already in Singapore and also open to some collaboration here, and also happy to if anyone would like to use Evomass in Singapore, because when I was doing my PhD, I have 1 year stay in Singapore. So the building in Singapore is actually inspired me a lot when I developing the Evomass. So that's it of my presentation. Thank you.
Okay, thank you, Dr. Wang.
Thank you.
So we will move on with Dr. Chen.
Okay, so I will just share my screen with. Is it working? Can you guys see?
Yes,
all right, so thanks for inviting me for the talk. So today my talk title is Algorithmic Architectural Design with Python Packages. So so I'm Kian Wee. I previously I was a postdoc in NUS, and currently I'm a postdoc in Princeton University. And so today I'm going to talk about some of the works I did during my PhD back in Singapore using the Python library. So essentially, the core of my research has always been trying to more effectively use algorithms in the design process. So the main core idea of why do you want to use algorithms and data and models is essentially you free up resources. So instead of having to do not very productive work of manually 3D modeling or manually searching for designs and so on, as what Likai has shown, a lot of the steps can actually be automated because they are routine tasks and they are extremely repetitive. So if you can effectively use algorithms and apply them in the design process, so you can free up a lot of resources from the designers, and instead of doing laborers and manual work, designers can actually take more time to make the creative leap and perform reflection on the design and so on. So let the computer do the difficult to do the repetitive tasks, and let the designers do what designers do best, being creative and designing. But of course, in our current design process, it's a lot of things is still very still done manually, and so we strive to incorporate algorithms as much as possible into the design process. So some tasks that can be assisted by algorithms are like site analysis. So if you make use of GIS system and you can get base maps and so on, or geospatial data from the Open Singapore data portal and so on, you can actually do a lot of analysis quickly with a GIS system and with all the tools available, Grasshopper, Dynamo, and so on. Evaluation, of course, modeling a design and then sending it to a simulation, and then evaluate it and understand how your design is performing. So Likai's presentation actually, show a lot of that. So, and then parameterizing your model so that you make it a single concept, that you parameterize it so that you can generate many designs just by changing the parameters. For example, the height, the length, the width, and so on. And you can generate multiple design variants and then send it to the simulation model to evaluate it. Then you automate this whole process. So you just by changing a few parameters, you can explore like multiple designs. And essentially, what Likai's tools can do is put it in the optimization algorithm, and then it automatically search for the best or the optimal design for the design problem that you have formulated. So there's many tools to do this, like Grasshopper, Dynamo, Python, and so on. So, but today, because Python is the tool that I usually use, I'm the most comfortable with. But the design process that I'm gonna describe, you can do it with Grasshopper, Optimal, the Dynamo environment, and so on. So, so don't let not knowing Python stop you from engaging in such a design process. So this is the library that I use for myself. I kind of develop it over the years, over my PhD and over my postdoc years. And if you're interested, you can search for it. It's called Py4Design. It might still be a little bit difficult for someone else to kind of quickly use it because I think I'm the only person in the world that's using it. So, but so I would advise you to use Grasshopper and so on to engage in such a design process if you're really interested. So I'm going to present a work that I've done. So this is mainly for my PhD project, where I use optimization algorithm to integrate engineering system performance into the design process. So here I'm looking at cooling systems and how the interrelationship with the envelope of the building affect each other. And one of the main issue of doing this is it's hard to for designers to actually formulate the design problem. So as you can see from Likai's presentation, there's a lot of steps involved in setting up a design problem to be optimized. And I think in Likai's work is very appropriate to what is happening now. So he kind of simplified a lot of the formulation work and make it much more easier and more accessible to the architects to use it. So for me, during my PhD, because I work with a bunch of group of engineers, and we were looking into novel cooling systems, so the use of radiant cooling. So this is a HO optimization problem. So if you want more daylighting, you let in more heat. And you let in more heat, you increase your cooling energy consumption. So it's a two contradicting objective that you try to optimize. So you want enough daylighting, but not too much cooling. So so that's kind of the whole point of the optimization is you want to balance these two main objectives. And this is mainly done through usually in architecture design is done through passive design. So you try to design good shading, well insulated and so on. But in my PhD, the idea was that what if you integrate the cooling system into the optimization? If I use a more efficient cooling system, so can I use a little bit less insulation and use a better cooling system, and then I can have more varied design. I can have more interesting building form, building envelope, and so on. So first of all, you have to define the cooling systems that I'm working on. So on the right is air conditioning. That's the most conventional cooling system that's being used in most tropical countries. So you throw cold air into the space and then you cool down the person. But for radiant panels, essentially you use radiant cooling. So you are actually cooling the occupants not through air but through radiation. So essentially how the sun warms you up is through radiation. So you're exchanging heat with the sun through radiation. And essentially for the cooling panels, it's the same idea. You're losing heat to the radiant panel, and so you get cool. And radiant panels are usually much more efficient, because if you look at the diagram on the right, air conditioning uses 8 degrees Celsius of chilled water to cool down the air, dehumidify the air, and throw it into the space. But if you use the radiant panels, there's a potential for you to separate the dehumidification from the sensible cooling. So for cooling the person in terms of temperature, you just need 18 degrees Celsius. And then you can have a separate system to throw in only very minimal amount of dry air to maintain the humidity. So you use 18 degrees Celsius chilled water to cool, and then another minimal amount of 8 degrees Celsius chilled water to dehumidify. So from doing this, you actually save a lot of cooling energy consumption, and the system is much more efficient. But there's a limitation to using radiant cooling. So because radiant cooling, you're exchanging heat with the surface, so you need to have enough active surface to cool down the space that you're trying to cool down. So that is architectural limitation. If your let's say if your room is at the corner of the building where it's exposed to a lot of sun, so the load is so high, so no matter if even the whole ceiling is covered with radiant panels, it's still not going to be able to remove all the loads. So that comes the problem. So when you're designing the building at the early stage, you want to make sure that your form is well designed, so that the loads would never go over the capacity that the radiant panels can give. So that's kind of how I formulate the design problem. And so in the optimization, it automatically chooses the cooling system for you. So if the load is within the capacity of the radiant cooling panels, we will be using a high efficient radiant cooling system. If the load is too high, we will just use the conventional air conditioning system. So that is integrated into the evaluation of the cooling energy consumption. So that's the two objectives that I'm trying to optimize. Lowering the cooling energy consumption while maximizing the daylighting within the building. And so you make a 3D model, and then you have to pass this 3D model to the tool evaluation with the right properties and so on to do the evaluation. So I'm going to demonstrate this in a project which we did a few years ago, the 342 design project in UWC. So the first step to run optimization is you need to parameterize the design. So you need to be able to decompose your design concept into a series of parameters. And I think that's what Likai's book was trying to address, is that's the kind of the more difficult part, like how would the architect be able to decompose their design to parameters. And Likai's plugin was trying to make it more automated. But in my example, I did the decomposition. So I first of all, I tried to generate the footprint of the building with 4 parameters, and then you can shrink the footprint and create the courtyard, and then you extrude up to create enough floor area, and then you can decide on the window wall ratio and the glazing materials and so on. So with this parametric model, you can generate many different designs with different forms and envelope and so on. So once you have the parametric model, you have the evaluations, you put it into the genetic algorithm to explore. So what essentially in a genetic algorithm, what does it do is you put in the parametric model, it generates many design variants. So it evaluates it, and then it has some mechanism to choose which one is the best. And then it would choose the strongest, and then it will crossbreed and mutate. So essentially the different parameters. So for example, if one design variant has 10 parameters, so I find 2 design variants and I cut in the middle, and then I change the parameters, and then I would generate a new design variant from the parametric model. And so I generate a new generation again, I evaluate it, strongest and so on. So, if you're familiar with the whole idea of evolution, when you keep selecting the stronger design variants to breed, they breed stronger and better performing designs. So you go through many, many rounds of this, and you can generate essentially stronger, better and better performing design variants. So in this case, I generated 5,000 designs. And you can see so each dot here is a design, and on the x-axis is the cooling energy consumption, and on the y-axis is the daylighting. So daylighting, you're trying to maximize, cooling energy consumption, you're trying to minimize. So you can see the arrow, and this is the optimal region that you want to achieve. So you can see from the optimization, it is actually moving towards that, right? So it's trying to optimize to achieve maximum daylighting and minimum energy consumption. So on the right, it's a blow up of the 3 clusters. So we can see 4 clusters here, 4 very clear clusters. And so I have to explain the Pareto front. So Pareto front is essentially design variants approaching the optimal region. So for design variants that's on the Pareto front, so they are kind of the best performing designs, because we have multiple objectives, right? So you cannot say which design is better than which. So all the design variants on the Pareto front are equal, because if you look at E is performing better than G on the y-axis, but worse than G in the x-axis. So essentially they are the same. You can't say E is better than G or G is better than E. So they're all kind of best performing design variants. So you can look at the Pareto front. Once you generate the design from the optimization algorithm, the easiest way to do is just look at the design variants on the Pareto front, and then you can kind of try to choose from there and develop further. But what is actually more interesting is, since this case study, the clusters are so clear. So let's look at a few designs from the clusters. So we use clustering algorithms, and we use filters to kind of filter out some interesting design variant within each cluster. So you can see in cluster 1, so it's very high performing. So it's performing very well in terms of daylighting, and it's performing quite okay in terms of energy consumption. Not as good as cluster 2 in terms of energy consumption, but the daylighting is performing quite well. So you can see there is characteristic to this set of designs. So they are all north-south facing. So if you have, we all know in Singapore that long north-south facing building is the best. So you avoid east-west facing elevations, and you have quite big courtyards and so on. So, and you have, all your windows are shaded, all glazing materials are using the best glazing material and so on. So you can achieve high daylighting and low consumption but then you can see the forms are quite similar, right? So if we look at cluster tree, so we are sacrificing maybe, you know, not that much of energy consumption, you know, like 2-3 kilowatt hours per meter square. We can see more varied form here now. So we can see the same form here, but using you know, not as good performing glazing material. And but then if we use quite good, so if we look at this design, which is quite different from the rest, we have glazing material, we have good glazing material. You don't really need to shade everything, but you still can have like a kind of like a different shapes and so on, and you can kind of explore different design variants. And then if we look at other clusters, so cluster here is cluster 3 and cluster 4. So cluster 4 is the worst. So these are the design that is, you know, using air conditioning instead of radiant cooling. And cluster 3 is, you know, doing quite okay. It's not as good performing as cluster 1, cluster 2. But if you look at an interesting point that I'm trying to say is that if you dig into the design variant, so if you look at cluster 3 and cluster 4, design variant 331 and design variant 205, they look the same, right? So why is it that design variant 205 is in cluster 4 and design variant 331 is in cluster 3? The only difference is the glazing material. So here it provides a very valuable insight for architects, right? So if, let's say, I'm going for this building form, just by adding a better insulated glass windows, I can achieve this form and then had a huge jump in energy, in reduction of energy consumption. And kind of that's a very key valuable insight for me. So let's you know, the optimization process can reveal this if, you know, you take the time to explore design variant and figure out what's happening at each different clusters, each type of performance clusters. It can actually reward you and provide you insights into spending so much time in running the optimization algorithm. So that's the end of my presentation. So I just hope that, you know, this kind of shows you what are the stuff that can be done with optimization process, and what feedback and insights it can give you when you apply it in the design process. So there's still some work that needs to be done, I feel. So currently running an optimization process is still not as intuitive as it should be for designers, because the whole process of decomposing a design into a parametric model, it's still not that easy. So it's not just about learning how to code. It's about a difference in way of thinking between designers who usually starts with sketches, you know, or a very rough 3D model, as compared to you know, encoding it as a design problem, which needs to be very clear. It needs to be encoded well. It needs to be generating sensible designs and so on. So there's a huge gap between these two, where you have a concept and then you try to decompose it to a design problem. So I think there's still a lot of research work that is required to make this gap, you know, close this gap, make a better interface for us to engage optimization algorithm. And another thing to look at is to try to make optimization algorithm run faster. So currently, you know, you might probably run an optimization algorithm once or twice in your design process. But imagine if you can run 10, 20 times, right? So if I have a new idea, as long as I have a new idea, I can throw it into optimization process and get back 1,000 more variation of that idea. So every time I have a new idea, I can throw in and get back more, regardless of the details. So for example, Likai's project is mainly working on the early meshing design. But what if in the later detailed design stage where I'm more interested in just changing building materials and so on. So can I quickly throw in a model and get back 1,000 design back and see what does it mean? So I think that would be the future direction on how to use optimization better. And I will end my presentation here. Thank you.
Okay, thank you, Dr. Chen. Okay, so for all of the participants, we have keyed in both Dr. Chen's and Dr. Wang's work, right? For example, the Evomass as well as Type for Design. So feel free to go and check them out. They are all free for all to use. So we are now open for Q&A. We have around like 13 minutes left for Q&A. Anybody? So now you can unmute all of your microphones so that we can. If you are shy, you can also type inside the chat box for questions. Okay, or maybe I'll just start the ball rolling, right? So one question that I would have for Dr. Chen, right, is that you mentioned earlier that you're probably the only person using that Type for Design now. Other than the GitHub, right, do you have any other resources where they can like maybe like some YouTube videos? I've seen Dr. Wang's website. He has some YouTube videos on how to use his library. Do you have any for yours, or you are intending to have any for yours?
So currently, not really. So because I'm the only one who's using it, and then I have a limited time to do all this. I would like to do it, but yeah, it's even maintaining the library would take some time and so on. So that's why I encourage people who's interested to engage in such a design process, to use Grasshopper Dynamo, where there's a lot of help and there's like a more user-friendly interface. But even in Python itself, there's a lot of optimization library. And there's also like kind of a geometry kernel like Python OCC and so on that you can use to build models and run optimization. So kind of the advantage of using Python is because anything that you want to do, someone else has done it before. So that's kind of why Python is so popular, because it's easy to find existing library that someone has used. Yeah, so you will still need some work to engage this if you're interested.
Okay, cool. There's a question from the floor now from Cheryl. So she was asking, what would your recommended steps to move from Grasshopper Dynamo to Python, or any useful resources?
But so but then I would reply with another question. What do you want to do in Python? So do you want to do optimization process, or why do you want to move to Python? That would be my question, because I mean Python is a general programming language, and it can do a lot of stuff. So and my advice to anyone who wants to learn coding is to have a project in mind. So don't learn the language for the sake of learning the language, because it will take you forever, because there's so much thing that you can learn about a language. But if you have a project in mind, that you have an aim that you want to achieve, and then you try to achieve it using Python, and I think that would be the easiest way to go into learning programming. And also, if you're using Grasshopper or Dynamo, Dynamo, I'm not sure, but Grasshopper definitely have a Python, have an Iron Python API, right? So that you can use. So you can start from there. If you want to learn Python and you already know Grasshopper, I would say use the Python API in Grasshopper first, and then get familiar with what Python can do, and then you can move on from there.
Okay, so she has clarified that it's more for optimization and building analysis. And Dr. Wang also has very kindly put in the link for how you can start learning for Python within Grasshopper. So people who are interested, you can check this out. Yeah, and another way is that okay, some shameless selling. BCA Academy, right, also has some computational beam courses, right? And during those courses, we introduce not just Rhino, Grasshopper, but also Rabbit Dynamo and a little bit of Python. So that would be good for people who are more accustomed to learning from an instructor versus self-learning. And it's also useful because at the end of the course, you have a group project, and then you will start to learn from other people from other parts of the discipline within the construction industry. Okay, and the key thing, as I think the interesting thing that Dr. Chen has pointed out, right, is more about how you are able to reprogram sort of your design thinking to the basic principles, so that you can really approach design from a parametric point of view. So you break down like a very big design problem that you have into how you want to arrive at this particular design. Then you can come up with the algorithm. So if you start thinking in that way, then you'll be a faster bridge for you to also adapt to using programming within computational design. So again, all these resources that Dr. Wang has put in for you. Dr. Wang also has a YouTube channel where he shows some of his use cases for Evomass. I think those are very interesting for you to start off with. So feel free to check out the links that we have shared there. Okay, now there's another new question from Karik. Is there a community in Telegram or WhatsApp or other platform where we can exchange more info and help each other? Okay. Yes, that is a very interesting suggestion. What I have currently now, because I'm also part of SIA, Singapore Institute of Architects, right? We have this Telegram channel for young architectural students, whereby they talk about Beam and Grasshopper, and I'm there as like a moderator. If you have any questions, you will post. So yes, so there is a community, but that's now for students. We can also open this up, but I will check with our SIA first, and also with Woodway, how to publicize this. But yes, we are trying to grow the community. If there's any news, please do come back to our, there's also a YouTube channel for this particular computational sharing. It's called Practice Beam. So if you subscribe to the YouTube channel, you'll be tuned in to any updates of whether or not there's a community or what is the Telegram channel name. Okay. Any other questions for the floor? How about for Dr. Wang? Oh, Woon, you are muted, so you need to unmute.
Hi. Sorry, I'm Woonwei. I'm from DG. Actually, I have one question. So the question is actually for Dr. Chen side. So is in US, right? How is the situation? I mean, for now, we understand it's a research component, but how about the practical side? So how was it being used for this? I mean, the use of Python. Are the designers really using it? So how I mean, for now we are. I mean, we're trying to just kickstart this, right? Since 5 years ago, the concept, now we're trying to engage this approach. So we would like to know, I mean, how is the scenario in US for this computational design and approach?
In Princeton over here, it's still, most people are still using Grasshopper. Grasshopper is still the common. I think Grasshopper and Rhino is still the industry standard over here. But definitely I see more computational designer positions in US where they are actively expanding their computational skills within the company. So like, SOM, like Gensler and so on, they all have computational design units where they have a whole department that is supporting designers. So they kind of differentiate designers from computational designers.
I see.
Because you do need kind of more expertise and technical knowledge in using computational design. And the other approach that I've seen is, I think in Singapore, you have the digital blue foam, and in US, you have Cove.2. So these are essentially companies that focus on building tools and putting everything onto the cloud. So essentially, they sell you the service and they streamline the whole computational aspect of it for you. So you kind of just log in to the web page, to the cloud. You can run optimization process and so on. And even if you look at Revit now, the latest Revit, edition already have optimization algorithm built into the software. So I think it's, I mean, one thing, one approach is, what Aloysius was talking about, you kind of do parametric thinking and so on. But I think the other approach is, if you just wait a few months or few years more, essentially the software are becoming more and more streamlined for designers to use it more naturally and intuitively in the design process.
I see. So another question for Dr. Wang. So for NUS, for the local Singapore, right? So I understand you already created a certain tool for design optimization. So do you see the new, I don't know, the undergrad, they are capable of creating their own tool for design instead of just doing design in production, right? For my generation, is just using pen, pencil, draw the thing. Now we are like creating scripts, then the script will do the thing. So it's like creating a small tools. Then with the tools, then you open up a lot of different potentials. So how is the NUS side, engaging this approach? So I understand you're going for postdoc already, very high level, but downstream, I'm not sure what's the scenario in the IHL. So how is the education moving on forward in NUS? So this is a general question actually.
All right.
Your understanding lah, yeah.
Yes. Well, I guess the same in China or in the Singapore, because the student is quite because architecture education is a lot of different stuff here, theory and things. So there's a very few students will be interested in the computational design. So don't to mention the developed tool, but I work with packages, and so I see. Some of his thesis, master's student is actually developing different tools for the architecture design. So I get, but they're just very a few, just like the 3 or 4 students will be doing the tools, something like that. But I guess it's already maybe a good start. Like at least some architecture student can be goes to the tool making, especially for the tool for the architects, because some of the tool, if developed by the programmer, maybe not very suitable for the architecture design.
Yes, exactly.
But if the student have the experience in the architecture design, maybe the tool may be more feasible or more easier for the architect to use. That's my observation.
Yeah, I have one more question. So, sorry for Aloysius actually. So actually for the practitioner side, right? Because you are the practitioner. So therefore, is your company, your staff, or are your staff, all the staff are capable of doing this, creating own script or yeah?
So
all my staff.
Yeah. Or most of it, I don't know how many percent.
All my staff, some Yeah. So again, it's kind of like Dr. Chen was saying, right? You have a designer versus a computational designer. So the designers will do the usual designing work where your time is already spent on coordination and managing clients, and then the computational designers, which are more dedicated to do this kind of work. So for example, last week when I showed the project, the 71 Robinson wrote the link page, right? So that one was done by one person who's just purely focusing on that. His name is Samuel Hardy. How we usually in practice, that's the only way to go, because otherwise the staff will have not enough bandwidth, and they'll be too zapped. Yeah.
Okay. Yes.
I can chip in here. So I think so. So for example, you say you can write a script, like write a tool, but you shouldn't think about like, oh, you write a script, that's all, then you can do whatever. So because like everything you need maintenance. So even Windows, even Mac, you have patches and installation. So imagine if a designer have to do this, like they don't have time. So if you write a script, it work for that project, then the next project doesn't work anymore, right? So that's why a lot of companies, what they do is they have a computational design department to maintain this. So, and then they see, oh, can this tool be maintained for all projects throughout the company? Because not all projects need this tool. So some projects are smaller, you don't need to do this and so on.
Okay.
So that's something to think about.
I think what happens here, there's still a gap, a skills gap, right? I suppose this is capability, is a skills gap, right? So if I can write script, hey, why do I want to use pencil? Or the thing is still... the importance, like what you mentioned, hey, these do not need that. So therefore, I don't know. So is a question.
But it's the same. So like I write a script and I pass it to Likai. Likai will have to spend a few days to read my script and figure out. So like it's not like a magical thing. You pass the tool and then someone else immediately can use it, right? So unless it's very well maintained, very well documented, and so on. So you need to think about it like that. Unless it's done, but that's why you have big software companies, right? Software companies that only maintain their tools and don't do anything else. So you cannot think like, oh, I read the script, the script can do everything already. It's a magic, like, no, it doesn't. So you always have to maintain, right? So, but then in terms of capability, from my understanding, SUTD is very strong in terms of teaching technical tools and Grasshopper and so on. So like their graduates are usually quite strong in terms of coding and so on.
Okay.
Yeah.
Thank you for your...
So in the middle ground between this, right, having a custom script, there are also sort of pseudo scripts called the Dynamo Player or the Rhino Player. So some firms now do use this to automate certain things. Like for example, just automate placement of lighting fixtures or automate generation of fire zone diagrams. Okay, so that's another bridge. So as opposed to the more high end that Dr. Chen and as well as Likai talking about in terms of design, where you generate the design, that one is a very complex script which needs maintenance. But you also have script in another sense that it automates the mundane things, right? So which is where Dynamo Player comes in, Rhino Player comes in. So again, there will be someone who is more adept at this computational beam tools like Dynamo, then they package it to become a Dynamo Player. So this Dynamo Player is very easy to use. It's just using a software plugin within the Revit interface. They just press play and then they just play around with the slider bars to maybe generate how many light fixtures you need in this room. They will automatically put this out for you. Okay, let's move on to the next question. Very nice question from Romaldo about structural. So whether or not we can use computational beam for structural engineering and structural engineers doing analysis and design. I put in a very simple YouTube video that anyone can go and watch. It's by Arturo Dubevsky. So he just shows his process of how structural design can be used computationally for bridge. What I'm aware of, because as I mentioned, I teach at PC Academy. There's a lot of sign-ups now for the courses by structural engineers, especially from Arab. So I think they themselves already have their own department where they have people that are doing this computational BIM. And as I've just mentioned, one of my ex-staff who is now at Web Structures, they also have a dedicated department where they have computational design specialists. That's in Singapore. Of course, overseas, Foster, they have their own advanced geometry unit group for structural. So that's definitely the way to go now. Oh, okay. There's another question. What we are discussing here is almost like rocket science as compared to our daily task as practitioners, which almost like nearly Titanic screws. That said, we need to appreciate R&D so that the design technology can advance. Yes, so that's precisely the whole point of why we are having this community. We want to let all of us know, especially in the Singapore and local regional context, right? There's already this kind of software technology. We have to adopt this, otherwise we will always not progress. We will always be like the local registered QP instead of some architect coming here to design like the Nick Garden by the Bay or Marina Bay Sands. So if we want to push our capabilities levels, we have to adopt this rocket science and make it almost like that's a very commonplace thing for us, for the practitioners here in Singapore, because this is the trend. Okay. Any other questions or anything that you would like to add from Dr. Chen or Dr. Wang for this question?
Not really, yeah, but I think I agree with you. We shouldn't look at it as rocket science. It should be more integrated into the design process of architects daily, because there's a lot of low-hanging fruit, like you say, right? So a lot of things can be automated in terms, for example, like zoning, checking, let's say, or like car parking layouts and so on, which can be very low-hanging fruit that should be easily automated and designers shouldn't be spending so much time on doing. So, but yet we still don't see that happening. And it's essentially because practitioner think that, oh, this is totally, far away. It's still very, it's totally not from our daily practice. I think, which is not true. So I think a lot of these things can be applied currently now in the practice. It's just really finding the right opportunity and really putting it to practical use instead of just generating very fancy looking design. You can actually greatly improve the efficiency of design process in the industry.
Hey, that's another question from George regarding software such as Pathfinder for simulation, example, emergency escape scenarios and human behavior able to be integrated with the BIM model, especially in the context of performance-based fire design of buildings. Wow. Okay. Yeah, I'm not so familiar with Pathfinder. Are any one of you familiar, Dr. Chen or Dr. Wang?
I'm not familiar, but I noticed there's some research done by some professor from the UK. Some tools called the Topologic. Is a tool they develop also in the Python, in the Grasshopper and the Dynamo. Is like I saw some cases and examples they are using it to do the fire escaping optimization, something like that. Maybe you can take a look on that. I will check the name for you and put it on the discussion the message box.
Oh, okay. Okay. So there's another question from Cheryl to both of our speakers. So she was asking from both of you from academia, how can we encourage practitioners, corporate firms to make use of computational BIM in practice, especially now that we have more graduates with computational background? yeah, so your current educators, how are you?
If you ask me, then if you're in the position to hire those people, appreciate their effort and their work, so and give them the chance to prove themselves and let them run some computational design for you. Because I have tried to apply some of the computational technique in practice. It's very difficult because of the schedules and the pressure of delivering and so on. So I think if you are really interested to expand on this for your practice, I think you kind of really had to set aside some resource, which is, I think, not an easy thing to do for a small practice, let's say. But yeah, so I think the attitude is next time if you meet a graduate with the right background, try to appreciate him and or her, and try to let him or her do a project, test out a project, and see how it works for your firm, for your practice.
Yes, that's a very good point. Always nurture your talents.
Well, and I guess even in the past, maybe 1 or 2 decades, I guess there will be a huge separation between the research community and the practice, I guess. And I never saw any practitioner to come to the computational design conference in, let's say, the Cadre one. So, but for the moment, I guess with more graduates with the computational design background to go to the industry, might be the situation will be changed in the near future. But the thing is still that maybe the superior need to encourage or provide opportunity for the young designer to use the computational design, because we have some graduate students from the Nanjing in China, and after they finish their master, they will go to the design firm, and then they just go back to the normal and the traditional way of using the CAD rather than using the Super. So it's
yeah. So I think from my side, that's one thing is, so if you look at the industry in US, where they actually have computational designer title, right? So that is something that, if you're a practice or you're a bigger practice, let's say in Singapore, consider that, having a computational designer title, consider thinking about, if someone was to invest their time and go in and become a computational designer, what's their prospect? Will your company actually provide prospect to someone who, take the effort to be a computational designer? What's their next step? Because if you're a computational designer, do you become QP? Do you not become QP? And what would be my title be? And only if you start appreciating people like that and you start giving them a career path, the industry will start to grow and start to embrace computational technique more. So you do need to give them a proper career path and prospect, which is, a much bigger problem for the industry.
Okay. Yes. So Boone also he said that yes, we have a BBM career track now recognized by Building Singapore. Yep. Very good. Very good step in the right direction from our government agencies. Okay. Any other questions? So now we 1:15 already. So if no last questions, yes, thank you. Oh, yeah, everyone should go and check this out. So thank you to Dr. Chen and Dr. Wang for your insights, especially from the academic point of view, and also your opinions of how this should be influencing our practice as well. So thank you, everyone. as I've already put in the links for all of their great work as well as our channel. This particular session is already recorded and it will be uploaded onto the channel for all of you to share with any of your friends. So we will have this session again next month. So feel free to stay tuned. We will be sending out email to those who have already subscribed to the mailing list that's organized by Boon. Okay, so thank you everybody. Thank you, Dr. Chen again. Thank you, Dr. Wang, for your valuable time. Okay, bye.
Bye.
Thank you.